We have a quorum. It's 5 after, so I will sort of start rolling. All right, so welcome to part 2 of, Brain Diversity, Information Theory. Links are here. I actually use the same slide deck to expand the slides. So if you want to follow along, you can go there, go/Brain Diversity Info Theory. Go Brain Diversity Info Theory PS is the problem set that we were talking about, which now, to clarify, I'll produce the solutions for the office hours in a couple weeks. And then, just to remind you, Go Brain Diversity Chat is the chat room to talk about the solutions or anything else related to the course. Let's see if my computer does stuff. Okay, so first bit of an errata. I think I told you it was Cleveland, Ohio, and Hackett'sville, New Jersey. It's actually Cleveland, Tennessee. Oopsie. So just as a little bit, because people showed some interest. So the distributions and stuff was coming from this Quartz article about somebody who tried to measure the colors. And I think I read it a while ago. The article's from 2 years ago. And apparently the original version of the article made the same mistake I did, calling it Cleveland, Ohio, not Cleveland, Tennessee. There's links here to the articles if you want to follow them. But I myself took kind of a spoonful of my own medicine. I bought a pound bag of M&Ms, and over the last week, my son has enjoyed having M&Ms with dinner most nights, and we keep track of colors that have showed up. So for our particular bag, there were 605 M&Ms in these colors. And I guess maybe just to illustrate the same kind of problem we were talking about last week, would ask the question, is it more likely that the bag came from New Jersey or Tennessee? And so we could just kind of go through this, right? Here are the expected distributions of colors for the two factories. Here's the weight of evidence, right? 10 log 10 of the ratio of these two probabilities for each color. And given my observation, I could take, 87 times 0.035 plus 69 times negative 0.2, etc. And for this particular case, I accumulate 93 decibands of evidence against the hypothesis that it is New Jersey over Tennessee, or equivalently 93 decibands of, or 94 decibands of evidence that it came from Tennessee. And the kind of smoking gun is if you check the back of the package, you look at the serial number. The serial number has CLV for Cleveland. So turns out weight of evidence worked. The well goes a little bit deeper in the sense that I started analyzing the distribution of colors I saw, and I'm seeing a modestly large deviation. I guess we could have expected that, right? So, before when we were computing the KLs, we said that the expected weight of evidence per M&M was something like 0.1 deciband, and there were 600 M&Ms, so we might expect to have accumulated about 60 decibands of evidence, and here we have 90. And it's a bit larger than we expected. And that corresponds to, if we look at the sort of distributions, they're off a little bit. And if I, do some simulations and I ask, if I actually had a distribution that was equivalent to the one that I say is Hackett'sville, and I simulate 1 million bags, and I ask how large I could see as large of a deviation or larger than I observed in my data, it happens exactly 0 out of 1 million times. Meanwhile, for the Tennessee bag, I do observe deviations as large, but they only occur sort of 2% of the time. So they're a somewhat rare event. And this has led me to think that maybe they have shifted their color distribution since 2017. And so I contacted Mars Corp and asked them, and they were wholly unhelpful. They refused to tell me the color distribution. So I wanted to give you guys an update. Unfortunately, I emailed them. They were no help. I called tried to call their customer hotline, got a dead end. I called the shift manager at the Tennessee plant, and they didn't pick up. So I will not rest until I get to the bottom of this. Fear not, but it'll have to come later. Okay. So another thing I just wanted to clarify a little bit, because I don't think I did a good job of talking about this last time, was, and I just want to maybe reiterate. So, because a lot of people also asked about multiple hypotheses, and we're going to talk about that in a second, because I think it's a fantastic segue into entropy. But I wanted to clarify that, there was sometimes when we were comparing sort of two different hypotheses, and then other times when we were comparing sort of that something happened versus the thing not happening. And I think the best way to think about it is just our beliefometers, in the way that we're talking about it, just have two ends. There's the right side and the left side. And you can kind of place whatever hypothesis you want on the right or the left side. It could be the bag of M&Ms came from New Jersey, or the bag of M&Ms came from Tennessee. Now, the two ends of the belief meter don't have to be exhaustive, right? You could do like, it'll rain tomorrow versus it'll snow tomorrow. Now, it doesn't have to do either of those things, but you could still have your belief meter have those two ends, and you could collect evidence, and the evidence could give you a weight that moves you left or right on this meter. But then sometimes we want to talk about like a single event or like a single thing. And so we just make the two ends of our beliefometer that the thing happens and that the thing doesn't happen. Like those are sort of our two hypotheses, right? You win the lottery, you don't win the lottery. And then we can interpret decibands as sort of like a probability, just on a different kind of space. Now, so yeah, I just wanted to kind of like, I feel like I didn't sort of say that, and I wanted to say that, but a lot of people, yeah, okay. And to kind of like maybe summarize what we did last time, we mostly talked about weight of evidence. It's just the log of the ratio of probabilities from one hypothesis to another. And you should think of that as information, the information that data provides in favor of one hypothesis against another, right? How much you move on the beliefometer in light of data. And then we talked about relative entropy, which is, or KL divergence, which is an expected weight of evidence. If one of the ends of the beliefometer was true, how on average, per observation, how much would you move to the right on the meter? And we talked about some of the properties that this thing has. It has to be positive, which kind of makes philosophical sense. Like if one of these two things is true, you should move towards the true end. And it's nice that that kind of works out both mathematically and philosophically. We talked about other ways to try to interpret KL as the only possible, like the magnitude of an update when you modify your beliefs from Q to P, and that it shares certain properties that we would expect, and it's sort of axiomatically the unique function that does those sort of things. So that was all sort of last time. And now, so this time I want to kind of talk more about entropy and mutual information and time permitting, which I'm nervous there won't be, but start getting into some more applications and stuff. And a question that came up a lot last time is what happens if you have more than two hypotheses that you're interested in talking about? And there's like a sense in which we can do this, and we can talk about it kind of more precisely. So imagine you've got an exhaustive set of hypotheses. Like, let's say instead of testing models now, like let's say I just like the hypotheses might be even simpler. Like I have this dice. Let's say I roll it and I have my hand over it. Like there are 6 different hypotheses that are exclusive that I could form, right? That the die is showing a 1, it's showing a 2, a 3, a 4, a 5, or a 6. And like the data I could collect is I could lift my hand, and that's going to provide some evidence for one of those 6 hypotheses being true, right? The hypotheses now are like, they're very simple. They're just a statement about which of the 6 things happened. And they're exhaustive in the sense that, unless whatever, some, I don't know, asteroid crashes through the window or something right now, like the dice is definitely showing one of these 6 things, and we'll be able to tell. So let's just look for a second at what happens in our sort of framework. So we said that the posterior log odds for one hypothesis versus another is the weight of evidence plus the log of the prior odds, log odds. And what we're going to do, since we have multiple hypotheses, is why don't we do the following? Why don't we do one versus all? Not one versus other, but one versus all, because that'll make things simple. So we're going to take as our first hypothesis that the dice is showing a 1. And then as our second other end of the beliefometer, we're going to do it's a 1 or a 2 or a 3 or a 4 or a 5 or a 6. Now, why would we do that? We're going to do that because this formula is going to simplify. Because the probability that it's a 1 or a 2 or a 3 or a 4 or a 5 or a 6 is 1. And the probability that it's a 1 or a 2 or a 3 or a 4 or a 5 or 6, regardless of what the data is also 1. And so if I kind of manipulate this formula, this term is going to go to 1, this term is going to go to 1. And now let's just look at what the weight of evidence is. The weight of evidence takes on this form. So if I'm comparing one of an exhaustive set of possibilities and I ask how much evidence does an observation give me about which of the exhaustive set happened, it's this ratio, the log of the probability that you observe that thing given that one of the hypotheses was true, divided by the prior probability you assigned on that hypothesis. And it gets even simpler if we imagine that the observations are discerning, right? When I lift my hand off of my die, I'm not going to be confused. I'm going to be able to tell which outcome it is. And like in particular, if I lifted my hand off my die and it was a 1, the probability that if it was a 1 that I saw a 1, I can take to be 1, right? If the die is actually a 1, the fact that when the photons hitting my eye suggests, or I have the experience that it's a 1 is going to be probability 1 event for the simple case. And so this gets even simpler. And for discerning data in the sense that I am just asking like a simple question, like which of an exhaustive set of things has happened? How much evidence, how much information do I collect when I observe one of those things? It takes the form of just the log of 1 over the probability I assign to that thing. And so this sort of generalizes. If I've got a random variable that takes on a discrete set of values, like x lives in some space tilde x, and I observe that x takes on a value little x, how much information have I learned upon observing that the variable takes on the value? The information I gain is log of 1 over p of x, the prior probability I assigned that it would be in that thing. This is what people often call surprise, because it kind of corresponds with surprise, right? The amount of information I learn upon making an observation is sort of inversely related to how rare I think that thing should be. If the prior probability assigned to the event is quite small, then I gain a lot of information when I observe that event. Like the surprise is large. I've learned a lot about the state of the world because I've just observed a very rare event. Meanwhile, if I had the probability is quite high, especially as it approaches 1, the amount of information I observe when I make the observation, it tends to 0. Like I've learned nothing because a thing that I expected to happen just happened. So the surprise, you can either write it as log of 1 over p or as minus log p, right? Those are the same. And that I wanted to do that. So where do we get here? So again, like a very special set of multiple hypotheses might be an exhaustive set. And in an exhaustive set, we could ask the question, let's use our existing beliefometer weight of evidence type framework, and let's ask a question, how much evidence, how much information can I collect for one of the exhaustive set being true versus any of them being true? And in that particular case, we're asking a very sort of particular question. When I observe the value of a random variable, how much information do I gain? And that surprise is log of 1 over p. Entropy is expected surprise. For a random variable, it is in expectation how much you expect to learn about the state of the random variable. In expectation, when I flip this dice, how much sort of surprise do I accumulate? How much information in expectation will I observe every time I flip the dice? That's entropy. That's entropy. That's one way to talk about entropy. We're going to talk about, just like we did with KL divergence, lots of ways to talk about entropy. But I wanted to start with this one, especially since people were asking about multiple hypotheses and things like that. So I want to say, I sort of did things backwards. Historically, entropy was the sort of first function. And even today, it's the most popular sort of information theoretic function that people talk about. And I instead started with sort of weight of evidence and relative entropy. And I think because those are sort of like, they supersede entropy. But just to let you know, entropy is sort of how things started. And in fact, in Shannon's original paper, much like I told you that relative entropy is sort of axiomatically pure and unique, in Shannon's paper, he was sort of after some measure he could assign to a random variable, not between two distributions, not between two hypotheses, but for a single random variable. And he sort of developed an axiomatic framework where he wrote down a set of conditions that he showed that entropy, this function of sum of p minus p log p, is the only function that satisfies all of these guys. It has to be continuous. Small changes in the distribution should cause small changes in the entropy. Should be monotonic for uniform distributions in the way that we talked about with KL. If I go from a lot of possibilities to few possibilities, that should sort of, the entropy should decrease. And it should satisfy a additive chain rule, much like our relative entropy did. Since we talked about relative entropy first, another way that we can kind of think about and gain some insight about what entropy is we can identify that it's just the relative entropy, but where we take as our alternative hypothesis a uniform one, right? If I ask in expectation how much evidence can I accumulate in favor of a hypothesis P against a uniform hypothesis, that KL divergence, that relative entropy is, you'll notice, the negative of the entropy of the distribution, and then there's a kind of constant offset, log n, that we get from the uniform distribution, the number of distinct possibilities there are. So the kind of sign flips and stuff, but the intuition is there, right? Last time we talked about relative entropy, what it can do. and how you can think about it as trying to discern between two different hypotheses. Here, entropy you can think about as being related to your ability to discern the model from uniform. You can tell the difference between the thing being uniform and the thing being P, if the thing is actually P. The last sort of connection, right, and throwing formulas around, is if we start with the relative entropy and you just kind of split it into its individual pieces, you'll notice that, you know, P log P over Q, it has a part which is negative entropy. We talked about that before. But if there was some other distribution Q there, you could still talk about relative entropy as being composed of the entropy and, you know, what people normally call the cross entropy. And I just, you know, because we hear about cross entropy all the time, I just wanted to kind of connect the dots here. Cross entropy is the thing that links relative entropy to entropy. It's the thing that links KL divergence to entropy. It's the, you know, difference between those. Okay. The traditional interpretation of entropy is as a measure of ignorance. And that's what I kind of want to talk about now. It tells us how much stuff there is in a random variable, how many sort of independent events there are. It tells us about how expensive it is to save things on the disk and how expensive it is to sample from the distribution.
Alex, can I make a quick comment about the previous slide?
Sure.
So cross entropy is also appears a lot in machine learning as a loss function. And
Yep.
This slide is actually very useful in understanding why we try to minimize cross entropy, because there is like the model distribution and a ground truth distribution, and we actually want to minimize the KL divergence. But
Exactly.
Because the entropy of the ground truth is constant, we can ignore that, and instead we minimize the cross entropy, which is the difference between the KL divergence and the entropy.
Amen. This is why, yeah, I tried to talk about that very briefly last time, and we're going to return to it this time as well. But KL divergence, because of, you know, that I think we've developed the most intuition for. It's a distance between sort of two distributions. It's how large of an update there is. You can really use it as it really is underlying sort of all the loss functions that we use in machine learning. You have something like P, which is the real world, Q, which is your model, and you want your model to be as close to the real world as possible. And what Majid just pointed out is if P is the real world and is fixed outside of our control, then this entropy term is a constant outside of our control. And so minimizing the KL divergence is equivalent to minimizing the cross entropy. And that's why that's so ubiquitous as a loss function. And we will kind of get back to that. I want to end with that and exploring that more deeply and talk about VAEs and stuff. Okay, so I want to talk a bit about this interpretation of entropy as a measure of ignorance, as like how much stuff there is, how complicated a random variable is. And so we're just going to try to work through some examples. Here, plotting this function, right? The sum of P log P for just a coin. So this looks like P minus P log P minus 1 minus P log 1 minus P, just as a function, plotted as a function of P. This is what the entropy of a biased coin looks like. If the coin is fair, so that it has a bias of a half, in bits, the entropy is 1. So every flip of a fair coin, like the amount of surprise, the amount that you learn, the amount of information every time you observe a fair coin is 1 bit, which hopefully agrees with some of your intuition about what bits are. As the coin becomes biased either towards heads or towards tails, on every expectation, on every observation, we learn less and less. And eventually, if the coin is perfectly headed or perfectly tails, we learn nothing because there was no surprise. There was nothing to surprise us anymore. For uniform distributions, the entropy is just the log of the number of elements in the distribution. You know, for distribution with 4 elements, it's 2 bits. For 8, it's 3. For 16, it's 4 bits. Just like relative entropy and stuff, you can measure this in other scales, decibands or Hartrees or nats, but bits are sort of convenient, especially when we're talking about coins and things. And so you should think about this. This agrees with your sort of, if I wanted to play some game of like 20 questions or something, if I wanted to uniquely discern an element in a collection of n things, how many questions does it take? Well, if I perfectly design my questions, every yes/no question can cut the space in half. And so the number of questions I need is logarithmic in the number of elements. So the entropy of a distribution you can think of as the number of optimally designed yes/no questions to discern one of the elements, to kind of pick it out. And we'll develop that a little bit more. 20 questions, right? 2 to the 20, if you remember the sort of mental math thing, 2 to the 10 is like 10 to the 3. So 2 to the 20 is like 10 to the 6. 20 questions can discern a 1 in a million thing. That's why that game is so powerful. With only 20 questions, you can, if perfectly designed, you can discern, you can uniquely pick out 1 in a million event. My advisor used to say log is a function like a chicken is a bird. It never gets off the ground. And I just wanted to kind of like give you a little bit of intuition for that. If you wanted to uniquely identify a human on Earth, right? There's 7.7 billion people today. How many yes/no questions does that take? Only 33. The log of 7 billion is only 33. So entropy is, it's both sort of easy to create. It's easy to create noise. It's easy to flip coins and generate entropy. And it's sort of very hard to, it often requires very few bits to discern even very large populations because of that logarithm. Okay, so entropy sets the fundamental limit in terms of how much we can compress data. And this is hopefully something that you're like aware of, and let's see if we can kind of like develop the intuition maybe a little bit more. So imagine I was just like playing some game. I was drawing cards off of a deck, and I wanted to take data and I want to like compress that data. I want to save it to the disk as efficiently as possible. So every time I draw a card, let's say I'm only interested in its suit. So I draw a card, I write it down. Okay, the first one's diamonds. I make a little text file of my computer. Diamonds, then clubs, then diamonds, then diamonds, then spades, then hearts, then clubs, then diamonds, etc. How much space on disk does this take? Well, okay, I did something very naive, right? I just wrote things in ASCII. So I can figure out in expectation, I expect each of the suits to be equally likely. So 1/4 of the time, I think it's going to be clubs. I used 5 letters for clubs, and each letter is 8 bits because it's an ASCII character. And then there's clubs and spades and hearts and diamonds. I take in expectation, there's 42 bits per sample. I'm spending 42 bits of my disk space for every one of these draws. So let's try something else. Let's be cute. Instead of using the words, let's use the Unicode characters, thinking I'm going to say space. Now it's a single character for each draw, but actually these Unicode characters take 3 bytes. And so, but I still save space. I go from 48 to 24. Let's do a little bit better. Let's use a single ASCII character, just D, C, S, and D. Now I'm actually using a single ASCII character, a single byte. So it's just 8 bits per character. And in expectation, it's still 8 bits. But I can do better, right? And I think since I've got 4 things that are equally likely, I could imagine designing a little tree. I've got 4 things. I could put them in a binary tree, and I could take as my code the path in the tree. So what's clubs? Clubs means I take the 0 path and the 0 path. So I'm going to represent a clubs with 0, 0. Spades is the 0 path and the 1 path. I'm going to represent the 0, 1, 1, 0 for hearts, and 1, 1 for diamonds. This way, if those really are bits on disk, for every one of my samples, I'm only using 2 bits. And so in expectation per sample, it only takes 2 bits. This is the best I could ever possibly do. And I think it's sort of easy to see that by construction. If I have 4 things that are equally likely, I'm going to need 2 bits to discern each thing. This is the entropy of this distribution. A uniform distribution of 4 things is 2 bits. Now, that's easy, but let's imagine, a non-uniform distribution. I have a biased deck. I have a deck where clubs happens a half of the times, spades a fourth of the times, and then hearts and diamonds 1/8 of the time. What can I do now? Well, if I use the same code, I could still use the same code, right? 0, 0, 0, 1, 1, 0, 1, 1 for the 4 suits. What would it cost me? Well, it's 2 bits per sample, and I weight the samples. Now I weight them unequally. They still add to 1 because of the probability distribution, so it costs me 2 bits per sample. The question is, can I do better? The answer is yes. The entropy, we might expect that the entropy of this distribution, which I can compute, p log p, summing over all the p's, is only 1.75 bits. So how do I do that? How can I use fewer than 2 bits for samples from this distribution? The answer is you just make a weighted tree. Because the events aren't equally likely, we don't need to use the same length code for every event. And so if I set up my tree this way, now I could use as my code for clubs 0, my code for spades 1, 0, my codes for heart 1, 1, 0, and for diamonds 1, 1, 1. And half of the time, I'll end up with a 0. Half of the time, I'm only going to take 1 bit. A fourth of the time, it's going to take 2 bits. And an eighth of the time, twice, it's going to take 3 bits. In expectation, this thing would only use 1.75 bits. That's the entropy of the distribution, and that's the fundamental limit. That's the most I could compress this data. here's what it would look like. It's a variable length code. But somewhat interestingly, not only is it a variable length code, but I can get rid of all the new lines because it's unambiguous. It's a prefix code. I can just read the sequence, and I just need to kind of take paths through the tree. So I read this thing. It starts with 1, 1, 1. So I start at the top of my thing. I go 1, 1, 1. Okay, I write down a diamond. What's the next character? It's a 0, 0. So I start up here. I do a 0. Oh, that's a club. I write that down. Then I have a 1, 1, 1 again. That would give me a diamond. And I can unambiguously decode the sequence. So entropy is fundamentally a measure for a random variable of how, it's a data compression limit. It's how compressed you can make the samples from that distribution. It's how expensive it is to identify which sample happened. It's also the number of bits it takes to sample from the distribution. And that, I think, is easy to see if we just ask, like, how could I draw samples from this thing? Like, how many coin flips would it take? How many coin flips would it take per sample I wanted to generate? Well, if I use the same tree, I can generate fair samples, right? And what's the procedure? I start at the top, I flip my coin. If my coin is heads, I call it a clubs. That'll happen half the time. If it's a tail, I flip another coin. If that coin's heads, I call it a spade. I took 2 flips. If that coin's a tail, I flip it again. If it's a heads, it's a heart. If it's a tail, it's a diamond. How many coin flips does that take per sample? Half of the time, it takes 1 flip. A fourth of the time, it takes 2. And an eighth of the time, twice, it takes 3. That's 1.75 coin flips per sample. Entropy is the fundamental limit for compression. It's also the fundamental number of coin flips per draw. It's how much entropy, it's how much randomness you need to draw a sample from distribution. So entropy is a measure of how much stuff there is, how big a sample is, and how much it costs to draw a sample. I just said that. Are we good with that? Speak up, please. I mean, yeah, feel free. Again, I guess I didn't say at the beginning, but please interrupt me and stuff like that and all this good stuff.
Well, I can only speak for myself, but I can say that this is the point where everything you've said up to this point makes sense. Every time I've read something of this sort, it makes sense. And yet somehow it feels so magical that everything, all these puzzle pieces seem to fit just right. And I struggle at this point to come up with an intuition on why that necessarily has to be the case. Like it doesn't quite feel like a proof in my head yet.
Yes.
It's just, I know this to be true. People have told this to me to be true countless times, so I trust it to be true. But I don't know more than that.
What is there? No p equals a half for the top node. So who is that asked? So okay. Thank you, Daniel, for the comment. I'm going to try to do a little bit better than that. I don't know if I'm actually going to succeed, but in a second, we'll try to go even a little bit deeper, and we'll try to sketch out the math reason why this happens. And I won't do perfect justice to it, but I'll make an attempt.
My stupid question was, what if the probabilities that you picked weren't so nice? Like you picked
yes.
like this nice. Like how would this look different?
So yeah, so in general, you can prove that you can do within sort of 1 bit of optimal. So if the distributions aren't perfect powers of 2, then this particular scheme isn't going to work, but at most it's going to cost you an extra bit per sample. So it's still quite good. And there are schemes that aren't this. This is what's called Huffman encoding, like Huffman trees. There are schemes that can do better. But at worst, it costs you an extra bit if the things don't round right. And that's kind of like picking up the errors you make in rounding, basically. So, yeah. Okay. So I'm going to try to get into a little bit deeper. Like Daniel said, we'll talk about the asymptotic equipoise here, but I wanted to stop here for just 1 second and give another interpretation of relative entropy. So we just talked about entropy as being the sort of encoding costs or the compression cost of samples. And so if you can ask, let's say I have draws from some distribution P, but I design my encoding scheme using some other model Q, how bad is that? How much of a mistake do I make? And the cost of encoding draws from P according to the model Q would be given like this. The cost, you should think about the surprise as the number of bits it takes for each sample according to that model to encode, because up to kind of 1, it's true. And so if I had samples from P and I'm paying a cost of log of 1 over Q, this is the expected cost of encoding samples from P using a model Q, some compression model Q. And you'll notice that this is the entropy plus the relative entropy, because I would just be adding, I'd be adding and dividing by a P. If I put a P here and I put a P upstairs and downstairs, the one downstairs turns into the entropy, the one upstairs turns this thing into the relative entropy. And so I just wanted to give that last interpretation. Relative entropy, you can think of as an excess cost associated with choosing the wrong compression model. If you had the right compression model, the cost of encoding things is entropy. If you have the wrong encoding model, you have to pay extra. How much extra? Relative entropy extra. And I just kind of wanted to say that because you might have heard that before, and I think if you ruminate on it a little bit, it might. Okay, so let's try and can relative entropy be negative? No. And the easiest way to think about that is in terms of its expected weight of evidence. I don't know if you saw last time but relative entropy has to be positive.
Sorry, the reason I asked is you're trying to encode distribution P in terms of distribution Q's. What if Q had fewer bits than P? That's what I was trying to. So is it information loss at that point?
Well, so in some sense, the mathematical fact that relative entropy has, but if you use the wrong model, it's going to cost you more. And that agrees with that. In some sense, that's a proof that entropy provides the ultimate compression limit. Like if we agree that this is the cost of using model Q to encode P, and we agreed that on the definitions of entropy and relative entropy, and we believe the math fact that relative entropy has to be positive, then you can take this as a proof that entropy is the compression limit. Maybe that's one way to try to satisfy Daniel. I don't think it's a particularly deep way, but it's one that we can already sort of understand. Because relative entropy has to be positive, and that's just a statement about log being convex, ultimately, if the cost is entropy plus a positive thing, the smallest that could ever be is the entropy. Entropy is the compression limit.
Okay.
And that just hinges on being able to sort of read this formula.
Okay, thank you.
Yeah. Okay, so I guess that's one way to maybe Daniel could speak for himself, but that's hopefully maybe gave it a little bit of a sense of, one way you could try to prove this thing, as long as you have an interpretation of all these things. But yeah, okay, let's try and do something else. Okay, so asymptotic equipartition theorem, another thing Shannon proved in his original paper, and I think it's sort of the core mathematical notion underlying all these things, compression and encoding and all this stuff. So I think the idea is quite simple. So the idea is, okay, the weak law of large numbers. What's the weak law of large numbers? It's a big name for a simple thing. The simple idea is if I take an average and I make it big enough, that approaches a mean. Like averages become expectations in the limit of infinity. That's the weak law of large numbers. That's just averages become means. Averages become expectations. If that's true, then we can just ask about a particular kind of random variable. Let's imagine I have n samples from a distribution, and I evaluate its joint density. The empirical average joint density for a collection of samples is going to approach its expectation. And the expectation of this thing is the entropy, if the things are independent. For independent draws from a distribution, right, the log of the probability of all n things happening is the product, or the log of the product of the probabilities happening. The log of the product is the sum of the log, and the average of the sums of the logs will, with many samples, approach the expectation of the logs, and the expected log p is the entropy. So this shouldn't be sort of controversial, this statement, but it has a profound effect. And the profound effect is that for very long sequences, we can say something very special about many draws from some distribution. And there's lots of things we can say, but they all kind of hinge on the idea that there's only very few sequences are typical. Typical sequences are ones for which, if you evaluated their density, you can say that their density is sort of within epsilon of the entropy. We know that with infinite samples, the joint density, the log of the joint density will approach the entropy. And so we're going to define sequences that are within epsilon of the entropy as typical. So then the thing that happens is those typical sets almost always happen. Like the weak law of large numbers in the infinite limit sets in, and because almost all sequences have averages that approach, because the averages approach the mean, everything is near the mean. All sequences that you observe, almost all of the time, are going to be typical. The number of elements of the elements of the typical set are equal probable, because they were all defined to have joint densities that are the entropy, right? Like they can only be within epsilon of one another, so they all have the same probability of happening. And the number of ones that happen is given by the entropy, because we now have a uniform population of things, and each of them have uniform probability. The densities that we can assign to them are the entropies, and so the number of them are 2 to the n times the entropy. So the asymptotic equipartition theorem is really just, again, the statement that averages approach expectations. And so if I ask about a particular thing, namely the joint density of n samples from some IID process, I can say that it should approach its expectation. Its expectation is the entropy. What does that mean? That means for lots of samples, they're almost all going to have densities that are close to the entropy, or n times the entropy. And all such sets have the same probability of happening, and there's only 2 to the nh of them in a sequence of n. To like show this, like let's say I have a coin, and the coin has a bias, and I'm going to choose the bias to be 11%. Like it's 11% heads. Why did I choose 11? Because then the bits turn out to be a half. Now, let's say I flip the coin 300 times. The Bernoulli binomial distribution looks like this. If I flip a biased coin with 11% bias 300 times, you would expect to get 33 heads. And that's where this mean is. The distribution is also pretty tight. I can ask, what's the likelihood of each? What's the most likely sequence of 300 coins that all have, that are 11% heads? What's the most likely sequence? What has the highest likelihood?
All tails.
All tails.
Yeah.
Exactly. Here I'm plotting the likelihood of each sequence. The likelihood is just, the fraction of them, it's just the fraction that are p times 1 minus the fraction that are 1 minus p. The most likely sequence is all tails, because tail is the most likely outcome. The least likely thing is all heads. And the likelihoods just look like this sort of straight line in terms of the number of heads. What's the entropy of the distribution? The entropy of the distribution, because I chose 11%, you work it out, p log p, 1 minus p log 1 minus p is a half. And that's right here. If I draw a dashed line, I take the entropy and I'm going to go 0.1. I'm going to make an epsilon that's 0.1 above, 0.1 below. So like I'm going to allow, 0.1 entropy up, 0.1 entropy down. I cast out this, I group these elements. If I ask for all of the sets of heads that have entropies between 0.4 and 0.6, that is 94% of this particular distribution. Almost all sequences are going to be close to 33 heads, and close in the sense that the entropies are all within 0.1. So almost all of the time.
Question.
Yeah.
Or whenever you finish your thought, and then I'll ask my question.
So yeah, so I wanted to. So now let's talk about how many things there are. So how many possible sequences of 300 coin flips are there? There's 2 to the 300. If the entropy is a half, and I guess I didn't show it here, I probably should have, but you can, you can use the choose function. You can actually count how many things are in here. How many things are there that are within 0.1 epsilon of this thing? Turns out to be 2 to the 300 times 0.5, which is 2 to the 150. The number, 94% of this probability distribution is made up of only, and I say only, right, 2 to the 150 possible sequences. Now, 2 to the 150 sounds like a big number until you hear the next number. How many possible sequences are there? 2 to the 300. 2 to the 150 is 10 to the, 2 to the minus 150th, a fraction of the total possible sequences. Almost all of the time is made up by a vanishing fraction of all possible sequences. Only 2 to the 150 possible sequences out of a possible 2 to the 300. And so almost all of the time, you're sitting in this exceedingly small part of the space. That's the kind of central point.
So my question, Alex, is this feels like really, really close to the central limit theorem in some sense. And I'm sure the connection is very strong, but can you elaborate on the connection as being, I don't know, somehow utterly more obvious or maybe more connected in a mathematical sense than just a...
Yeah, I mean, so I didn't really want to get into it. All we need, in some sense, this is an easier statement to prove than things like the central limit theorem, in the sense that all we're using with the weak law of large numbers, why is it weak rather than the strong, is that we're saying that this thing converges in probability. So we're not actually necessarily saying that this thing converges to the specific value, only that you sort of like can't tell the difference asymptotically. The probability that you're different from this value vanishes as you collect an infinite number of things, and that's a weaker form of convergence. Like the normal law of large numbers and things like the central limit theorem are proved by, or they hold in a weaker set of, they hold very generally, but they require a stronger sense of convergence that we have here. We only require that like the probability that you differ from this value vanishes as you collect an infinite number of things, not that you actually approach the specific value. And you can kind of come up with some examples where, you can approach a value that you can't actually have because it's knocked out of the thing, but still you can't tell the difference. But I sort of didn't want to get into those details, but like, I guess I want to say, like, in terms of like central limit theorem, law of large numbers, convergence of means and stuff, all the stuff that we're using the same things here. We're actually just using an even slightly weaker version of any of those expectations you have about the world or reality. Now, so yeah, the central result, again, just to kind of, because I do think it's kind of like important, is that if you have n samples from a thing, the joint density of those n samples, there's sort of three things that we can say. The typical set made up of those joint sequences that are within epsilon of the true entropy are almost all things. They have probability of like 1 minus epsilon of being in that set. They are all equal probable, sort of by design. And the number of elements in there is 2 to the n to the h, which is much, much smaller than 2 to the n. If the entropy is not, 1, basically. So for this particular case of a coin, again, like I flip it 300 times, how many possible sequences is there? There's 2 to 150. That sounds like a big number, except that's nothing compared to 2 to 300. And so the reason compression works, the reason coding theory work and things like that is because you can design a very naive scheme that basically achieves optimal compression asymptotically. And a very, very simple scheme, just like a thought experiment. Let's say I wanted to compress samples. What I could do is I could just separate the world into two parts, the typical set and the atypical set. And now how am I going to compress things? How am I going to like write down my samples? First, I'm going to use the first bit, 0 or 1, to say whether I'm in the typical set or not. Okay, that costs me 1 bit per sample. Now, if it's in the typical set, I'm just going to like lexigraphically order all of the elements in the typical set, and I'm going to index into that thing. How many things were there in the typical set? 2 to the n times h. How many bits does it take to pick that out? N times h. That's what the entropy was, right? It was sort of telling us how many questions it takes for me to, the log of that. That's how many questions I would need to identify. If it's not in the typical set, what am I going to do? I'm just going to enumerate all possible sequences, and I'll assign it an integer for that. How many of those are there? There's just a log of the total cardinality of my space. Now that's obviously like bad, except like almost all possible sequences, like with our coin flip, right? Of those 2 to the 300, that's going to cost me sort of 300 bits to say which sequence it was. But like that's almost all of the sequences. But at the same time, almost all of the time, I'm in this much smaller set that's only 2 to the 150. And how many bits am I going to spend to tile those? Only 150 bits. And so like this very simple scheme, if I ask how much does it cost to write everything down, the probability that I'm typical, if I'm in the typical set, it's only going to cost me the log of the typical set size. If I'm not in the typical set, it's going to cost me the log of the cardinality, and I paid this extra bit. And the way this whole thing works out is because asymptotically, the probability you're in the typical set is 1 minus epsilon. The probability that you're atypical is epsilon. If we kind of draw enough samples and we can set our epsilons to be small, this whole thing can scale like n times h plus epsilon, and epsilon can be made arbitrarily small. And that's sort of, this is what like, the reason this whole thing works is just this. Why does the +1 get dropped? I mean, I guess I shouldn't have dropped the +1. I meant the tilde to kind of do a lot of work. Usually you write the whole thing out, you put in all the factors, and then you replace epsilon with some like epsilon prime, which is just like some other value that epsilon could take. And you show that like you could always choose an epsilon that makes the other thing like, because of the way this thing is scaling, the 1 doesn't matter. If you deal with long enough sequences, the 1 drops out, right? It gets killed. It's not leading order. The n term, the leading order term in this whole expression goes like n times h plus epsilon, and all the other terms are subdominant. So the +1 is subdominant in the sense that as n gets large, the difference between 1 and a billion is a part in a billion. It's nothing to worry about.
So I just wanted to double check my understanding. I get a feeling that this approximation overall actually works if we assume that the sequence that you are coding is practically infinite, right?
So I mean that's like in Shannon's proof and stuff. Yes, like in the sense that this is a naive scheme, right? You wouldn't actually want to do this, but if you did this, even though it's naive, I think have just argued that even this naive scheme is in the limit that you take the block size, the number of samples to be large enough, basically indistinguishable from optimal. That's the kind of point of the argument. So it's to argue that, and like this is generally how these things work. If you have enough samples, if you have enough things that you're trying to compress, enough things that you're trying to write down, you can get arbitrarily close to like the entropy as the fundamental limit.
And that enough is like the length of the blocks also depends on the distribution, right?
I mean, there are universal codes that kind of work independent of like the thing that we just described as a universal code, and you could like look at how many samples you take,
I mean, in mathematical terms, if you sort of look at the formula that you had about like the epsilon, right, in the previous slides, that epsilon itself depends on the probability, right, distribution.
No, we chose epsilon.
Right, but then n depends on the distribution, right?
Well, n is also kind of chosen in the sense that we're trying to describe how many bits does it take under we tried to describe a coding scheme. What did we try to do? We tried to describe a coding scheme for writing down n samples from a distribution with entropy h. And the coding scheme that we decided on was, let's choose a epsilon. Let's separate the world into 2 pieces. The things are sort of within epsilon of entropy and everything else. And what's our actual coding scheme going to be? If it's in the typical set, you're going to lexicographically order only those typical sequences at the cost of the log of the size of the typical set, which is just n times h. If it's not in the typical set, you're just going to write the thing down in binary at the cost of log of the cardinality of the space. And the interesting thing is that scheme, as sort of dumb as it sounds, the cost goes like this. And the way that thing scales, like the leading order scale to that thing takes this form. And so if we sort of choose epsilon small enough and n is large enough, then the n epsilon term, as epsilon gets small and n gets large, the n epsilon term vanishes with respect to the nh term. That's the kind of point of the proof, right? Is that doesn't matter in the limit as n goes to infinity, that we can sort of choose epsilon to be arbitrarily small. And again, like I guess I don't like if you want the kind of details, like this isn't, I'm not trying to give a detailed proof here. You can read like Cover and Thomas and stuff, and you can like read the mathematical proofs. I think instead the thing to focus on is the intuition. Like, why is this thing happening? This is happening because if I draw many samples, ultimately, this is why. If I draw many samples, the density of the joint sample approaches the entropy in the same way that an expectation approaches a mean. And what that means is that the number of things that almost always occur is way, way, way smaller than all possible things. And so it's sort of cheap to only write down the things that are typical,
So
because
let's
they happen almost all the time.
sorry, I'm just trying to make sure that I understand this correctly. So the claim is that we want to prove that the number of bits that we use on average in our coding, on average, it can be as close as we want to the entropy, right?
In the limit of infinite samples, yes.
Exactly. So that limit that you say, that how large the blocks should be, is that independent of the distribution, or that depends on the distribution? That's my question.
For this particular scheme, I think it does depend on the distribution, like exactly the details of what n you would have to choose.
Okay. And then you're saying that there are other schemes that even n is independent of the distribution.
Well, I mean, I guess like there are other schemes for which the subdominant term of this thing can vanish much faster, right? In the sense that this scheme was designedly suboptimal, right? We only did two things. We asked one question: is it typical or atypical? And if it's typical, we do the dumb thing, and if it's atypical, we do an even dumber thing. There are schemes that instead try to utilize the shape of the distribution or knowledge of the distribution and do something kind of more intelligent. Like an example would be the Huffman tree, right? The Huffman tree, for a distribution whose probabilities make up powers of 2, this was a thing that could achieve exactly the entropy with no additional cost, and we could do it per sample. But what kind of Shannon showed was, for any distribution, independent of the distribution, there exists an n for any epsilon for which you kind of approach, like as n goes to infinity, for any epsilon, you approach the entropy. That's the nature of the claim.
Okay, thanks.
Okay, so this entropy is the sort of amount of stuff. It's how many things there are, like how many distinct things there are in a distribution. But I feel like that does require a little bit of subtlety. It's easy, like with our, because it's a little bit more subtle, right? In the sense that with our biased deck, there were 4 suits: clubs, spades, hearts, diamonds. The entropy was 1.75. 2 to the 1.75 isn't 4, but it's like 3 something. I should have calculated it. It's not that there's only 3 and some change different suits. There's still 4 suits in the deck. But in that distribution, if I had a long chain of draws, a long chain of draws behaves as if it came from a uniform distribution with only 3 and some change elements in it. For this coin, it's not as if, there's only 0.1 possible sides of the coin. There are 2 sides to the coin. But in a long sequence of draws, the rate of growth of the typical set goes like 2 to the n times h. H is a half a bit. The thing behaves as if there's only sort of a half a side per thing. I completely botched that sentence. Hopefully you understand what I'm kind of going for. The size of the typical set goes like 2 to the n times h, which is the same as 2 to the h to the n. If I had a uniform population of p things and I had n draws of them, how many possible sequences are there? There's p to the n. And I guess what I'm saying is the way you should think about entropy as a measure of how many sets there are is when I draw many samples, the rate of growth of the number of possibilities grows as if the thing only had p states, where p is 2 to the h. I think I botched that one too. Okay. I think this is a good time to take a couple-minute break so people can kind of get up, stretch their legs, and then we'll come back to it. So yeah, feel free to do that. And now I'm just going to kind of chat for. We'll officially start again at, let's say, 5 after. We'll take a 5-minute break. But at this point, feel free to draw your legs. We'll answer questions and we'll chit chat for 5 minutes. So I should put up a thing for break. Okay. So are there any sort of questions on that and stuff? And I mean, Daniel, did that help at all? Sort of get a little deeper, or help you kind of peek behind the curtain and see what might be happening in the math a little bit? No?
Yes. Yes. I guess I don't know how to put it, but the line between compression and measuring uncertainty in random variables still feels very magical, that these two things are so tightly interlinked, especially because when I think of compression in the practical sense, I'm usually thinking of real files on disk, which are very much not a random generation of random characters from some alphabet. Though if we model it that way, then it gives us the tools to reach for compression as a source of random variables and information. Another way to put it is, when I think of machine learning and like language models, I'm generating text, I'm typically generating sentences, and usually, every token depends on the previous one. It's very much not this ID kind of process that we reach for. And yet things like, typical sets are a typical set of possible responses is the kind of thing that feels so natural, but instead we reach for beam search, or we reach for greedy decoding, and we pull out, most likely sequences, which look exceedingly unlikely in the grand scheme of things. I guess the mixing of random variables and then compression and more fuzzy things of language models are they're all so tightly interrelated. And then toss in loss functions on top of that and cross entropy. And it's feels like so many different pieces are getting stuck together, and they're all so tightly related. But the stories behind them come from such different ways that it doesn't quite connect yet. And I really don't know how to. Yeah. I think this may not be this will not be the time that it suddenly clicks. Maybe it'll come sometime later.
Yeah. No, I mean, I hear you and I agree with you. And I mean, I think you should look at it as a blessing rather than a curse. The fact that these things are so related, you can stew in it and you can let those intuitions ebb and flow between the things, right? Try to think about the one in terms of the other and the other in terms of the first. And I think that can help, because they're so closely related, that actually helps you in the sense that it allows you to build stronger intuitions about the sum of the parts is greater than the whatever the saying is. some of the wholes part of the sum. I don't know.
Yeah. Right. Yeah. Thank you, Alex.
Yeah. Okay, so that went a little slower than I had maybe hoped. This always seems to, but yeah. And again, we're not going to start again for a couple minutes, but and I guess you guys could tell me different, but I wanted to make a point about continuous entropy and how much it's terrible, in my opinion, and then mutual information somewhat quickly, and then if we have time, and we might be able to talk about VAEs or ELBO as in terms of information theory, but we're not going to be able to do great justice to that. But I think enough to entice. Oh. And I'll be right back. But if somebody has a question, I should be able to hear just. Any y'all are being quiet today. Any other questions?
If I have time for a question, I'll ask a question.
Okay,
So
go for it.
This is kind of assuming that you know the probability of your coin prior to encoding it, right? Which you typically don't. How does that impact things?
Yeah, so I think that's a great question, and I think that is something I want to talk about more. But I think so. Yeah, with respect to learning and stuff like that, this statement again, in the sense that the best you can possibly do is if you knew the true distribution, and then the cost of encoding things is going to be the entropy. If you have the wrong distribution, the cost is exceeded by the relative entropy. And so maybe like as another way to try to motivate, why would relative entropy make for a good learning objective? It's because if what you're concerned about is learning how to compress things, how could you train a compression system? You could minimize the Kale divergence between, or minimize the relative entropy, which, as was pointed out by Majid, if P is fixed, the relative entropy is the same as a cross entropy. So minimizing cross entropy is like, in some sense, explicitly trying to design a scheme that is as compressive as possible. And the fundamental limit that you're pushing up against is the entropy of the distribution. So if you don't, that's the nature of things. So yeah, part of the problem, and I guess I haven't emphasized this, like all of this stuff is well and good, but like we very rarely know exact distributions, and so we very rarely can measure any of these quantities. But because relative entropy is always positive, we have like for free, we could generate arbitrary variational bounds. Like if there's a thing you don't know, the KL with respect to anything that you want has to be positive. And so if you minimize that KL, you know you're getting closer. Like it's we sort of for free have bounds because of the nature of KL being positive. And not doing that justice, but maybe we'll be able to get back to it. Okay, I think I'm going to kind of start going. So one thing I want to leave everybody with is continuous entropy. So previously, when we were talking about weight of evidence and relative entropy, because we always had these ratios of probability densities, it didn't matter whether we had discrete events or continuous ones. Because even for continuous probability densities, P of x dx, like the dx's would cancel. Dx, P of x dx, Q of x dx, the dx's cancel, and everything kind of worked out. For entropy, not quite the case. And continuous entropy for continuous distributions is kind of quite silly in like a weird way. So we talked about how relative entropy is reparameterization independent and permutation invariant. It sort of doesn't matter if you change your coordinate system, everything is the same. The same is not true for continuous entropy. That's sort of important to know. And it's sort of, I think, easiest to understand even if you just think in terms of like dimensional analysis. So if you look at we could try to define a quantity that looks like entropy for a continuous distribution by doing an interval. Integral dx, P of x, log P of x with a minus sign. What are the like dimensions of each of these, the units on each of these things? Let's say we're defining a distribution over like, over a distance. Then like, dx is a little bit of distance that might have like dimensions of distance. P of x is a density, so it has dimensions of 1 over distance, because we know that like the integral of dx px has to be 1. That's a number, that's dimensionless. The integral of a density per length times a length is dimensionless. So this thing has dimensions of like inverse length or inverse stuff. So then what the heck is a log of an inverse meter? I certainly do not know, because it's not really like a well-defined thing. Continuous entropy is weird. You can see that even for things like rescalings. If I take x and I rescale it by a factor of alpha to some y, how does that affect the entropy? If I go from the integral of dx px log px and I stick in y's everywhere, the dx px part, the alphas cancel, right? One factor goes into the density, you get one factor goes into the measure, the inverse of that goes into the density, and they cancel. But you have an alpha in the log term that never gets canceled by anything because we got rid of the guy in the ratio. And so we end up with the entropy of x being related to the entropy of y being off by a constant of the log of the multiplier. Like, what does this actually mean? This actually means that if you measure a real-world distribution that you think is continuous, the entropy that you assign to that continuous random variable depends on your units. So here's a distribution of adult human heights, which is bimodal, because men and women tend to have different heights. This is what the distribution looks like. What is the entropy? Like, you could literally like integrate p log p of this distribution. The problem is it depends on which units you use. So if you draw this curve and you read this axis and you measure height in centimeters and you integrate p log p for this curve, what do you get? You get 16.2 decibands. If you instead measure the thing in feet, you use this axis and you do the same thing, you get 1.3 decibands. What happens if you do it in meters? Meaning you like use this axis, but you measure that as 1.4, 1.6, 1.82, you get negative 3.8 decibands. Continuous entropies can be negative. What does this mean? This means, like, really, if you think about it, related to the way that was happening here with the rescalings, a continuous entropy is just a measure of the log of the range that the random variable takes. What's the range of heights in centimeters? they go from like 150 to 190. That's like 40 centimeters, right? What's the log of 40? Or 10 log 10 log 40? Something like 16. What's the range in feet? Heights go from 5 feet to 6 and change. So it spans sort of 1 decade of heights, one unit, right? Heights sort of span 1 in feet, and they span something like 40 in centimeter. And how much do they span in meters? They span less than 1, and the log of something less than 1 is negative. They span only like a third of a decade. And that's why the decibands, which are 10 times the decades, is -3. So beware of continuous entropies. I think it makes a lot more sense to really think about them as being sort of relative entropies in disguise, where everyone is supposed to agree on what the uniform distribution you're taking a distribution with respect to is. But if people disagree, it can have real consequences. So let's say you're doing things on like image space and you're reporting your likelihoods. If your images are defined in the interval -1 to 1 or 0 to 1 or 0 to 256, this actually changes your measure of the likelihood by either 0.7 nats or 5.5 nats per dimension. If you don't agree with somebody else that your images, like if your images are 0 to 1 and their images are 0 to 256, they're going to have a likelihood that's different by 5.5 nats per dimension. And I guarantee you that there are papers published that like compare numbers across conventions here. Guarantee it. I've seen it myself. So I like, honestly, if there's one thing that we could do, I think just anytime you report likelihoods, like at some point be explicit about sort of the units, or like more practically be explicit about what you think the uniform distribution is, like how it's defined. And like, I guess the difference is, right, a uniform distribution on 0, 1 is different than a uniform distribution on 0 to 256. They have different heights. And that's why these things are different. And if nobody kind of tells you which one they're using, then we got a problem. Yeah. Okay. Mutual information. The last of our kind of cast of characters. I want you to think about a thought experiment. Here I got my die. I roll the die. And let's say I tell you that the front of my die is a 5. What have you just learned about the top? We could plot a joint distribution for these two things. Like, let's say this is the top of the dice and this is the side of the dice. If the side of the dice is 1, well, the top can't be 1. And if you don't know how dice work, the opposites of dice are always add to 7. So if the front is 1, the top can't be 1, but also the top can't be 6, because the 6 has to be on the back, opposite the front. But it's sort of uniform whether it's a 2, 3, 4, 5. And the same works for all of these. So if I told you what the front is, you've learned something about what the top is. You haven't learned what the top is exactly, but you've learned something. How much of something have you learned? Well, let's say your belief-o-meter or something, if you started off with being completely ignorant about what the top of the dice was, in decibands, that's sort of 7.8 decibands of, uncertainty. 10 log 10 of 6. Once I tell you the front, it goes down to only 4. So it goes from 7.8 decibands to 6 decibands. That's a difference of 1.8 decibands. Me telling you the front has revealed 1.8 decibands about the top of the dice. The entropy, the uncertainty you had about what the top was, decreased upon learning another variable. You had the entropy of the top, h of x, was 7.8. The entropy of the top given the front was only 6. That difference is 1.8. That difference is the mutual information. The mutual information between x and y is the amount of information you learn about x if I tell you y, or vice versa, the amount of information you learn about y if I tell you x. Trying, it's in words, the mutual information between x and y is the sort of bits you learn about x after observing y, which you can think of as the reduction in the entropy. You had some uncertainty. There was a certain number of states that x could be in. If I tell you y, that might go down. If y tells you something about x, how much does it go down? The mutual information. If we look at the definition, This is the definition of the mutual information. And I think we can think about it in light of our other interpretation in relative entropy. So the mutual information is defined to be the KL divergence, the relative entropy, the expected weight of evidence between two hypotheses. The first is that the two random variables vary jointly. The other hypothesis is that they're independent and that they vary according to like their independent marginal distributions. So basically the hypotheses are you observe, like, let's say I gave you data, the data is pairs of fronts and tops of die. It could either be that I'm giving you fair options for what the, like pairs that were generated together. I actually flipped the dice and I told you the top and the side. That's hypothesis one, that they vary jointly. The other hypothesis would be I flip a die and I actually flip it twice. And I just tell you the front on the one dice and the top on the other. And they're independent of one another. And the expected weight of evidence, if the pairs are actually coming from a fair dice, the expected evidence you could accumulate per flip that they were actually varying twice rather than varying independently is the mutual information. And so this is a measure of how much you learn observing both the things together rather than observing them separately. How easy it is to distinguish between a world in which they're actually coupled and a world in which they're independent. So what are the natural limits here? What if the things are actually independent? What if for the true distribution, P of x and y is P of x, P of y? Well, then you have log of P of x, P of y over P of x, P of y. Log of 1 is 0. Mutual information is 0. If the two things are actually independent, there's nothing to learn. I tell you y, you've learned nothing about x. I tell you x, you've learned nothing about y. In the other extreme, if there's a deterministic invertible function between them, if I tell you x and you know y, then this joint distribution is a delta function, right? It's P of x delta of y, y is equal to f of x or something. And that delta function, log of infinity is infinity. You have an infinite amount of mutual information for a continuous random variable between them. I wanted to elaborate that later. I'm botching it right now. But this is, you can either think of mutual information as a reduction in the amount of entropy and very viscerally the amount of bits you learn about one variable and observing the other. But I also think there's a lot of utility in connecting it back to relative entropy because we proved a lot of properties of relative entropy. It has to be positive. Well, if relative entropy has to be positive and mutual information is a relative entropy, mutual information has to be positive. And you can start to build all the intuitions there. I also wanted to show you two equivalent ways to write it that connect with the other formula. So you can write this as, P of the joint, log P of the joint over P of the factored. If we want, we can just factor the joint and write it as P of x, P of y given x. So Laura, if you have a discrete random variable, then, and they're deterministic. So let's say that, like, what's the mutual information between the top of the dice and the top of the dice? Well, if I tell you the top of the dice, how much have you learned about the top of the dice? You've learned how much information there is in the top of the dice. But for the discrete random variable that is the top of the dice, that was only 7.8 decibands. And so the mutual information of a discrete random variable with itself is the entropy of that random variable. But for a continuous thing, like if I tell you x, what's the mutual information? I'll do this. I think I have another slide for this. It was much later. I did this in a bad order, but so I'll just say it. But let's say I tell you x and I ask what's the mutual information between x and like x squared. Well, if I tell you x, you can predict x squared exactly, assuming it's positive. That was a bad example. Let's say I tell you I tell you x and I ask what's the mutual information between x and exponential of x. Well, now if I tell you x, you know x of exponential of x exactly. If it's a continuous random variable and there's like an infinite number of digits there, then you've learned an infinite amount of stuff. And so the mutual information between x and exponential of x is infinite. Mutual information between the top of the dice and the top of the dice is 7.8 decibands. But that's just because there's only 6 possibilities for the top of the dice, and there's an infinite number of possibilities for x. Okay. Yeah, so I wanted to work through this just to sort of help you see the math. Again, it's not very important, and you can replicate it yourself, but here's the joint P of X and Y over P of X, P of Y. We can just write P of X and Y, we can factor P of X, P of Y given X. And we could write this as P of X, P of Y given X, but then the P of X's cancel. And this formula, hopefully by now it's starting to look familiar. This looks like a relative entropy between P of X given Y and P of Y. So the mutual information is either the relative entropy between the joint hypothesis and the product of independence, like marginals, or it's the expected relative entropy between the conditional distribution and the marginal, between what Y would be if I told you X versus what Y would be if I didn't tell you X, in expectation over all X's. And because it's of the way the formula is written, it's manifestly symmetric in the variables, even though our relative entropy was asymmetric between the hypotheses. The hypotheses here are the joint hypothesis and the independent hypothesis. But with respect to the variables, this thing is symmetric. And so I could either write this as the relative entropy P of Y given X, P of Y, or P of X given Y, P of X. And that sort of doesn't matter. You learn the same amount of information if I tell you one random variable about the second as if I tell you the second that you learned about the first. It's positive because relative entropy is positive. The amount of information you learn about another random variable when I tell you something has to be something or nothing. It can't be negative. Now, there's all these formulas connecting all these things, and you can like manipulate the formulas, but I think it's easier. There's a graphical way to represent all of these relationships. And it's just with sort of Venn diagrams. So the way you read things is, well, you've got a random variable X, and X has a certain amount of stuff, and you represent that stuff by an area. And so you write this, you draw this blue circle, and you call that entropy of X. And you've got another random variable Y, and that has some stuff, and you represent that stuff by some area, and you call that entropy of Y. And then you consider sort of all possible intersections, and all these intersections have names. Like, you know, these things could overlap, like the top and side of my dice. It's not that. Jointly, how many independent ways are there for tops and sides of dice to vary? It's not, you know, they're not 36 possibilities. There's only 24. And so the joint entropy is the area of both of these circles taken together. The area of the intersection is the mutual information. How much do I learn about X if I tell you Y? If I tell you Y, then you know they're inside this red circle. So now the space that is left in blue is just this overlap, and the overlap is the mutual information. The conditional entropies, how much do you learn? How much is left uncertain about X if I tell you Y? Is just this outer blue area. It's how much of X is outside of Y. And so all of these formulas, which are sort of easy to verify. H of X minus, yes, that's a typo. This should be H of X given Y, and this should be H of Y minus. All these formulas that are relatively easy to verify mathematically are sort of trivial to read off the diagram. What is the mutual information? What is this area? You could either think of this area as all of blue minus this outer blue, or you could think of it as all of red minus this outer red, or you could think of it as, you know, all of blue plus all of red minus all of blue and red together. That's the third formula. Or you could think of it as all of blue and red together minus all of the outer blue minus all of the outer red. And so these Venn diagrams are really the way that you should like reason about these formulas and stuff, because it's a lot easier. Although I want to caution you a little bit. I said that these things are like areas, and so it's easy to think that all the quantities involved are positive, but they're actually like signed measures. And if I intersect 3 random variables, the information theoretic quantity related to this inner thing can actually be negative. And I don't think you should ruminate about that too deeply, but you should know it. So just be aware. Not all possible like conditional entropies or mutual informations or 3-way mutual informations and stuff have to be positive. Although mutual information has to be anything that you can write as a KL does, and that's the only like rule. Okay, for our die, we had sort of 7.8 bits of air, 7.8 decibands of area for the front, 7.8 decibands of area for the top, but they overlap, and they overlap by 1.8 decibands. And that's kind of the nature of things. You've learned something when I tell you one about the other, but not everything. Okay, I'm kind of running out of time. This was kind of a cool example. Because I wanted to get a little bit, I want to at least tell you what a VAE is, and I'm running out of time. So I guess You can look at this. Yeah. Okay. Oh man. Yeah, I'm going to end with. Go ahead.
Just a small question, Alex. For would you be willing to record a like a missing parts section of you in a room or something of all the cool stuff that you were going to tell us but can't tell us because you're running out of time?
Yes, I would be willing to do that.
Thank you.
Willing to do that. Okay, so I think the thing I want to end with, ignoring some missing cool stuff, is I want to talk more about this relationship with other things in machine learning, because I promised that originally, and I think we can at least describe what an independent way of thinking about what a VAE is. So we've talked about this several times this time, but I think really starting with relative entropy as the kind of one of the primary characters here, we can invoke this as a principle of learning. The real world follows some distribution, and what we as machine learners do is we build machines. Those are models, and they have some distribution. As a principle for learning, what we can try to do is we could try to make our model most like the real world as possible. The interesting thing is now we have a mathematical way to characterize as close as possible, right? How do you measure how close as possible the model is to reality? Well, why don't we take the relative entropy between the real world and the model? Let's ask how easy it is to distinguish the two of them, right? How much of an update is there when I move from one to the other? Let's use this information theoretic, axiomatically unique function to measure the divergence. Then, as a universal sort of principle for learning, what should you do to your model? You should make it most like reality as possible. And mathematically, that means minimizing an objective of this form, where P is the real world and Q is your model. And as was pointed out before, right, Majid reminded us that if the real world is fixed, if it's something I can't modify, right? I can't go and actually, I'm not some genie or something. I can't change the real world. The P log P part of this, the part which is the entropy of the real world, is fixed and outside of my control. And so minimizing this objective is equivalent to minimizing this objective, which people call the cross entropy. And that is what people do. Cross entropy minimization is equivalent to KL minimization, which you now have, hopefully, a better intuition of why that's a good idea. What you're trying to do is make your model look like the real world, be indistinguishable from the real world, so that you cannot accumulate evidence against your model in favor of the real world when drawing samples from the real world. And in particular, maximum likelihood is a sort of distorted version of this, because we often don't have access to, we can't take expectations. And this cross entropy asks us to take an expectation with respect to the real world. We often can't do that. We often instead have a limited number of samples from the real world, and so we replace the true distribution with this empirical distribution. And minimizing this empirical cross entropy is an attempt. But if we're being honest, what it's actually equivalent to is not minimizing the KL divergence between Q and P. It's equivalent to minimizing the KL divergence between Q and P hat. If all we do without any form of regularization, without any control or care, is optimize the empirical cross entropy, we are asking our model to get as close as possible, as indistinguishable as possible from this horrible delta cone. A thing which says that the only thing that exists in the world is the training set and nothing else. There's no density anywhere else. It's exactly the training set, and the training set is all equally, uniformly likely. And like nothing else is possible. That's what we're asking our models to do. And oftentimes they do it to a degree that we don't like. Now, you can extend this principle. So that was just talking about a single density. And I want to end you with this. Imagine I have images in the real world. And let's say I want to do representation learning. I can augment the real world. I can't like change the distribution of actual images in the real world, but I can build something in the real world. I can add a thing to it. I can build a machine. But let's say my machine is actually a representation. My machine is a channel. My machine is a thing that takes an image and spits out a representation. It's a neural network that takes an image and spits out a vector. I can add that to the real world, and that can live in the real world, and I can imagine a joint distribution over both images and representations. A joint distribution over images and outputs of my neural network. And that can live in the real world. Now, I don't know the distribution of images, but I could know potentially the distribution of outputs of my neural network this conditional distribution. What's a model? What's a hypothetical? What's a kind of world? What do I wish the world looked like, but isn't true? I wished that I knew that like the output of my neural network was somehow representative, or it was like a latent factor. It was a thing that gave rise to the images. I wish that the world looked like I could generate samples of the outputs of neural networks and then somehow invert those to form images. That's what I wish were true. And so how can we kind of like bring this all to bear? Well, we have a thing that's true that we could kind of take samples from, and we have a thing that we wish were true. What should we do? Well, why don't we make our wish look as possible like reality as possible? How do we do that? We minimize the relative entropy between what we wish and what we got. This is Elbow. This is all a VA is. And I'm out of time. But I wanted to at least tease that. I invite you to, without having to think about generative modeling and variational approximations or anything, you can think about variational autoencoders as literally just making this look as much like this as possible. And I have run out of time. Now, I have made several promises. So yeah, I've got a whole bunch of other slides. I mean, like I could talk forever on things, blah, blah, blah. I do think I have some kind of cool things. I had some designs of trying to write up notes to associate with these lectures. Also, people are kind of free to go. So at this point, it's just kind of, yeah. But I'm happy to take questions. I'll hang out for a bit. Okay. And I'm trying to ask for advice. Okay. So what do I do at this point? So I've got the problem set. I could come up with other problems. It seems like so far people haven't engaged too much with the problem set. Maybe that'll change. I could write up notes associated with all the things I've kind of said in written form. I don't know if that'd be easy to look over. I could record me talking about other cool things that I might want to talk about. Each of these takes some amount of time. Could we have a discussion about which of those things you think you guys want, or et cetera, or whatever? And then also more generally, any questions you have about any of the things I talked about, now is your time. I'm here to help. Let's all, and thank you for listening, and all this good stuff.
Personally,
Okay.
I'm sorry, I'm the loudest person, but I'll speak anyway. First, I really appreciate video recordings, because they're the kind of things I can watch when I'm cooking. They're the kinds of things I can watch when I'm on toilet, I'll be honest. They're the kind of things I can watch in the shower. I don't literally have to be reading and concentrating and thinking very, very hard to be thinking about something. I don't have to look at something. That's very, very helpful.
Okay.
And so that is my motivation for videos over notes. Second, that notes are frequently written in a way that doesn't tell a story in the way that you're telling excellent stories right now. And so I really like videos.
Okay. I appreciate that. Okay. I will try to, low production quality, sort of minimally, maybe chat about the other slides I have here and kind of fill that out and send a link out, and people can, do what they want with that. I will sign me up.
I mean, if you say when you're going to do it, people may just show up and watch. Like I'd happily watch another lecture as well.
Okay. Is there, okay. Yeah. So I've got, okay. I appreciate that. I've got the kind of slides I've already prepared with some other kind of cool stories, but then are there things that people wanted to hear about that I didn't get to? I mean, I'm sure there's lots, but are there if there was, something that people want to hear me try to explain, I'd be happy to make an attempt to explain it in so much as I have the authority to try. So, I mean, just to give you some idea, right? Originally, I mean, there's other kind of maybe cool examples. I mean, just some other stuff about mutual information, but then really the kind of stuff that I'd originally tried to talk about is the thing that I just sort of teased, right? So I think going more deeper into variational autoencoders, how you can interpret them as variational bounds on mutual information, what they're doing, representation learning, then things like information bottleneck, information bottleneck, and later things like Bayesian inference as a form of information, blah, 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 blah. All that stuff is the stuff that I think I have the most things that I could say about. And so I'll try to do that. Okay. Thank you, everyone, for your time. Yes, and please ask questions. That's what I just wanted to, yeah, thank you. Go ahead.
Yeah, no, thank you. All of the things you just listed sound, amazing. I would personally like to hear those from a single perspective. Regarding the problem set, I engaged with it, but I have some anxiety in asking questions. I actually had questions about just what some of the problems were asking, making sure I understood. I guess what is your goal? What would the ideal engagement be? Like, what would you like
I
us
mean,
to ultimately get out of
no,
this?
yeah. I don't actually want to grade anyone's homework or anything, right? I guess like I guess the problem said, like, me personally, I find that like I learn best like kind of like working through things, and so I prepared the problem set sort of with myself in mind as a customer, in the sense that like these were actually some of the problems that like over the years I personally have like worked through, and I found the most like enlightening to have worked through. So like it's I guess like for that reason, it's the kind of thing that like I guess I'd be hesitant to actually like, you know, talk through all of the problems, because I don't think that's kind of the point, right? The point for them is to kind of like work through them. But like I guess like I wonder if like, you know, I'm kind of like whether there's an audience for that, right? In the sense that I think there's other problems that I could generate for other things where, you know, working through it, or like things that I work through that help me understand, and I could kind of like write those up. But and I can write up like solutions and stuff, but I guess like I would be a little hesitant to kind of like just talk through those, because I feel like that.
Yeah, no,
But certainly, if you have questions like about what things mean and stuff, like don't hesitate to bother me. Like, please, anyone here, if there's anything you want to talk about, or like I love talking about this stuff, so please just like ask questions. You know, whatever in the chat, reach out to me. You know, let's you know, especially in these COVID times, you know, I miss just chatting with people and micro kitchens and all that good stuff. So please, yeah, bother me. You know, don't consider it bothering. Just talk. Yeah.
Thank you, Alex.
Yeah. Thank you.
I don't know. Can I ask a question? So
yeah, please.
These formulas on the slide. So you're deriving the elbow without invoking Jensen's inequality. Is that
exactly? Yeah.
That's because Jensen's inequality was always the thing that struck me as like, why would you want to do that? That's a very, very bad inequality. But I'm very curious about this derivation then.
Yeah, no, I mean, so I think you're onto something, right? And this is precisely the thing, in the sense that VAEs are normally motivated as variational lower bounds on the marginal likelihood.
Yes.
And that's how they're done. But the problem is, like in our paper, Fixing a Broken Elbow, we try to like talk about this, right? In the sense that if you think about a VAE as optimizing the marginal likelihood, basically like, here, what do I want to say? Here's two very different models, okay?
Yes.
Like VAEs. One VAE would be like a perfect autoencoder. Like let's say I take an image, and as my encoder, I have a uniform, like an identity map. I take the image, and my latent representation is just the image. And then what does my decoder do? It does nothing. Okay, that has perfect reconstruction, right? In a sort of information theoretic sense, what has this thing done? It's distortion. I didn't get to talk about this, but it has perfect reconstruction. So this thing has on the zero on the y-axis, but it costs something, right? How big is that latent? That latent is as big as the image. It has the same entropy. So it's entropy of the image out on the sort of x-axis. But it has perfect likelihoods. The marginal likelihood for that thing is perfect. Here's a very different model that has perfect likelihoods. Make your encoder 4. Like throw out the image and just like, you know, 0, 4, 7, like a fixed number or an independent number. It doesn't matter. And as your decoder, just have a generative model that tries to synthesize a new image from scratch. Okay, what is the rate? Like how expensive is your encoding? Precisely 0, because I've done nothing. How good is your distortion? How likely are you to create the image? The entropy. Because like you're creating a randomly valid image. What's the chance that that image that you're generating from whole cloth is the same as the one that went in? You know, 2 to the minus entropy. Like it's small, but it's finite. Now that also has perfect marginal likelihood. So those two models are equivalent with regards to the marginal likelihood. They are exactly the same, but they're very different in this perspective of the KL divergence between these two densities, because those are very different joint densities. The one is doing something, doing everything. The other one is doing nothing. And so like, it's okay that like the VAE is a variational upper bound on the marginal likelihood. And that's one reason why you might think it's interesting. But I really think it sort of misses the point of representation learning, in the sense that like, you know, I mean, maybe sort of like more tritely, the fact that the marginal likelihood requires marginaling is out to latent should have been a signal that it doesn't depend on what the latent is. Like there's no requirement that that latent representation be any good, as that sort of thought experiment signified, because you're marginalizing out when you look at the marginal likelihood. And so even though, yeah, like I'm sort of trying to agree with you. I don't think the right derivation of a VAE is as a variation upper bound of the marginal likelihood, because that's true. But if you wanted to build a generative model, just build a generative model. The reason to do something like a VAE is precisely because you should be interested in trying to learn a representation. And once you do that, then you start to identify and be able to talk about what your representation is doing and how much information it captures and stuff like that. But that's sort of like, yeah, my own personal.
That's really cool. I wish someone told me that years ago.
Yeah, me too.
Can I ask a follow-up?
Please.
I think you kind of alluded to it, but there's also the question of overfitting, right? And if I understood correctly, I mean, if you go to that diagram, one of them basically completely overfits. It's the top left one. No, sorry, the lower right one, because it basically learns the full image as the latent, so it's kind of completely overfit. And I think you indicated a bit before, right, that basically there's a statistical argument how you can actually keep things from overfitting if you think about it statistically.
So yes, so I want to like broadly agree with you, right, in the sense that okay, so from the perspective of marginal likelihood, this model is precisely the same marginal likelihood as this model. They both have the same marginal likelihood, and so they can't be distinguished in terms of likelihood. But they are distinguishable, and that's, I think, what you're playing after. This model is like dumb in a real sense, in the sense that like if your latent representation of the image is as rich and just as complicated as the image itself, you've done nothing. But in order to distinguish that, you need to distinguish it in terms of a measure of how much you've kept. And that is the KL term. That's the rate, which itself is a variational upper bound on the mutual information that you've kept in the representation. And so I'm going to agree very strongly with you that, like, yes, the fact that nobody would really be happy with this model because it's sort of dumb is precisely the signature that we should be looking at some other measure than just marginal likelihood. Like, it is important to us that, you know, something like rate matters and that we should be aware of that. And once you have that, then like it's immediately clear that like you can imagine a trade-off between these things, and you do a beta VAE and all this other stuff. Now I want to like even double down and agree with you even more in the sense that if the point is to prevent overfitting, we can talk about you know, not just in the context of something like a VAE, we could talk about something like a parametric model, and we could ask questions about like how much information we extract from a data set into the parameters of the model and stuff like that, and think about those from a representational perspective. And that's a way to like motivate Bayesian inference as like a form of inference without having to do marginalization and blah, blah, blah. Anyway, so yeah. And that's the kind of stuff, yeah, I wish I could talk. Yeah, maybe I'll try and create a video to talk more about.
Please, 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 please. I absolutely love it. This has been so educational for me.
Thank you very much. I appreciate it. Are there other questions? I guess I wanted to. The important things, yeah, just to kind of revisit. Man, the computer's so slow. For the course, I thought I had a summary slide, but I can't find it right now. But I just, yeah, to recap, right? We talked about these sort of this cast of characters, and there were the sort of four of them. There was the weight of evidence, relative entropy, entropy, and mutual information. And if you get nothing out of this class, what I kind of hope for is that maybe now you have several intuitions and interconnected, better intuitions about what these four things are, how they might be useful, and how they're kind of connecting to stuff you're already doing, and hopefully things you'll do in the future.